Me too. Thank you very much to the organizers for giving me the chance to speak here and organizing this very nice conference. Right, so fall to the center and fall to infinity. Well, fall to infinity I will only put one slide on because it's on a poster by my student Sriram. Where is Sriram? Where is he? There he is. Okay. So his poster's out there, but anyway, I will advertise it briefly in there. So I'm new to the field of non-Hermitian systems. I must say I'm kind of confused between pseudo-Hermitian and all the different. There's 5 different definitions. So I guess my aim of the conference, my personal aim, is to try and learn exactly what system I'm talking about if it falls into one of these categories. So feedback is welcome. All right, so this is work that I did with my 2 students, Ryan Plested and Sriram Sundaram, who's here, and my colleague Cliff Burgess. And we work in Canada, where we like to cut down trees and sing. Okay. And the work. So this work is based on a preprint that's out there. So really, it's applying a method which is the baby of Cliff. Which is something called point particle effective field theory, to this fall to the center problem, and we have in mind an application to. Just saying, this says 33. How does that work? You let me know. Oh, it's the remaining time. Perfect. Gotcha. Okay, going backwards. Okay, so it's an application of this point particle effective field theory to this fall to the center problem, and in particular with generalizing the standard fall to the center problem to where most people try to regulate it to make it self-adjoint. We want to make it to allow it to be non-self-adjoint, so to describe absorption and things like this. Okay, so the plan is going to be, I'm going to describe fall to the center and point particle effective field theory applied to a particular problem of atoms interacting with a wire. And we'll look at some experimental consequences of the theory. There will be some. And fall to the infinity, as I said, we will just introduce very briefly. And to those who know me, I can't give a talk without mentioning quantum catastrophes, which is something I'm just obsessed with. And it's related to some of the things Michael Berry will say next week when he gives his lectures. All right, so this is on one slide what effective field theory is all about. So imagine you have an atom, okay, and so normally we might solve the Schrödinger equation, non-relativistic Schrödinger equation to describe electrons, and then you really don't worry about what's about the nucleus. You just say, okay, it's a first approximation, it's just it's just this charge that's sitting right at the origin. But then to the next approximation, you want to include the effects of the size of the nucleus. But it's on an incredibly small scale compared to, let's say, the electron orbit. So you can think of this as sort of the nucleus as the electron orbit. And we want to build in the effects of the microscopic physics on the very low energy electron orbital physics, and one under this sort of ordering of scales. And what we can do is, what we can say is that the effects, so you can sort of think of this as somewhat like a multipole expansion. So we can describe the effect of the nucleus on the electron wave function by some expansion, and this expansion, we can truncate it very early, basically because of these scales here. Okay, so you can check that, the whole point with point particle effective field theory is that you say, okay, the effect of the nucleus is really a sort of delta function sitting at the origin, and then to first order, it just depends on the density of the electron wave function there. And you can then add extra derivatives and extra powers and so on, but they're going to be smaller for dimensional reasons when you put in these ordering of scales. And we're going to match the two, so we're going to match the electron wave function to this microscopic physics at some distance. So we're going to apply some boundary condition on some sort of pillbox, some Gaussian surface, which is going to be much larger than the nucleus size, but still essentially microscopic for the electron. Okay, and so our total Lagrangian will be our normal sort of Lagrangian for our Schrodinger equation, but then we're going to add on this point particle one. Okay, and so, for example, one thing we want to describe with this is the problem of fall to the center. So imagine you have a particle being acted on by a central force, such that the angular momentum is then going to be a constant if you have a central force. Okay, so according to classical mechanics, then our energy equation is this: we have our kinetic energy, our potential energy, and then our angular momentum barrier. Okay, which goes as 1 upon r squared. Now we ask, under what circumstances do we have fall to the center? Well, if our potential, if it also went as 1 upon r squared, but with g, this coupling constant here, being slightly bigger, anything bigger than the angular momentum barrier, then it can fall to the center. Or, of course, you can have a more strongly singular potential, and then it will also collapse to the center according to classical mechanics. So the idea is that then we have this, we have a critical impact parameter, and if we're just less than it, we're going to collapse to the center. If not, then we won't. Okay, and in quantum mechanics, this is a well-studied problem. One needs, so after removing the angular part of the problem, you're left with the radial equation. And what you find is that when you have the power of n here, of this external potential, if n is greater than or equal to 2, as I said, as your sort of classical intuition works, you find that the energy suddenly becomes unbounded from below. So you get infinitely negative energies, and that's the manifestation of this fall to the center. And these bound state energies become continuous. And these are sort of problems for standard quantum mechanics. Okay, so that's why you don't typically see in most books, apart from Landau and Lifshitz, you wouldn't see them treating the 1 upon r squared potential, certainly in undergraduate books. So this is an example of what I call a non-self-adjoint problem. So which of these classes it falls under, I look forward to discovering. Okay, so this is a very well-studied problem going back a long, long time. If you've written a paper on this and it's not here, I apologize, and please tell me about it afterwards. So we're certainly not the first people to work on this by any means, but we're trying to apply this particular method of this point particle effective field theory, because the way people fix up this problem, in my opinion, tends to often be somewhat arbitrary. So people put various boundary conditions here and there, and we wanted to do a sort of systematic way so that if you were doing you were trying to predict some properties of having some finite size. I mean, so my colleague Cliff, he's interested in finite size of the proton and things like that. How you could tell experimentalists, what sort of things they should measure in a systematic way, how you build up these corrections of these multipoles. All right. So, but moving away from the sort of finite size of the proton, there is a problem which is much more realizable in sort of ordinary systems. So that and in particular, the 1 upon r squared potential, which is exactly this sort of critical case where it just collapses. So if you have an atom which is polarizable, so it's a neutral atom, but it's polarizable, and it's in the presence of a charged wire. Okay, so imagine this wire is infinite, so it's effectively a two-dimensional problem. It gets a dipole moment induced, which is proportional to the electric field produced by the wire and the polarizability. And then the electric field, then due to this infinite charged wire, it goes as 1 upon r. So when we combine these two, then the potential that the atom feels, minus half d dot E, will give this 1 upon r squared term. And this... we can get this, exactly this 1 upon r squared potential here. Okay, and then of course there's going to be some microscopic physics that we want to include for our point particle part to describe the interaction of the atom with the actual wire. Okay, but you can imagine the wire as we were at some very large distance from the wire, so we effectively see a 1 upon r squared potential right down to very small scales, which are our sort of high energy physics, if you like. Okay, so this system has been realized by these guys in Austria, Jörg Schmiedmeyer's group. And so they had a wire and they put a gas of atoms around it, okay? And they charged up this wire. And they can tune the charge by basically the voltage that they put on this system. And what they found is that indeed, so they shine a laser on it and they look at the fluorescence, and they see that the fluorescence decays with time, and this is due to the atoms falling onto the wire where they're absorbed at that point. Okay, so you find, depending on the voltage, you get this decay. So it's on a log scale, but it's an exponential decay of the fluorescence. And what they found was a very good match to the classical theory for the absorption cross-section of this wire, which in 2 dimensions becomes a length, which is kind of, as you imagine, twice this critical impact parameter. And interestingly, so it goes as 1 over the velocity of the particles, which is kind of what you'd expect. So as we'll see in a second, this 1 upon r squared potential has no intrinsic scale. So this is sigma being basically proportional to 1 over k, or the wavelength of the atoms. And so there's no intrinsic length scale in the system except what the atom has, that it's de Broglie wavelength. Okay. So there, as I sort of hinted at there's a scale invariance in this 1 upon r squared problem. So if you just take the Schrodinger equation here and you scale all length scales by lambda and all times by lambda squared, then because the 1 upon r squared potential goes as 1 over a length squared, and the Laplacian goes as 1 over a length squared, you pull out a lambda squared, and then if you scale time, you can bury that in the time, in other words, and you find that then this lambda cancels on both sides, this lambda squared cancels. So there's what we call classical scale invariance in this problem. So there's no intrinsic length scale. And by classical, I mean single particle quantum mechanics now. Okay, it's also it extends to the single particle Schrodinger equation, and it's also true in the classical mechanics. So this is interesting, but also a problem, because imagine so it means that if you have this scale invariance, if you can figure out a solution to this equation and you have a particular state, well, then you can get an infinite family of them just by scaling everything by this factor lambda. So that means in particular, let's say you find one bound state, well, then you have an infinity of bound states where you just scale all the energies and all the times, and that's outside of conventional quantum mechanics, that you have this continuum of bound states, whereas bound states normally should be discrete. It's a rather important sort of basic condition on them. So this is a problem. And this isn't the only system you can realize this scale invariance in. So another example is a 2D gas, which you can make. Here they've got a 2D gas of atoms held in an optical lattice, and you can squash it very flat. So it's basically 2D. And so at cold temperatures, you can describe the interactions by these contact interactions. And then this is a 2-dimensional delta function, which then also has a 1 upon length scale squared scaling. And so it's going to scale the same way as the Laplacian. Now this part, the harmonic trap, breaks that scaling invariance. But there's a very clever analysis of this problem by Pittievsky and Roche, and they show that there's a hidden SO2 symmetry in there, which basically means that, turns out there is a scaling symmetry, and it's to do with the breathing mode, sort of dilation and contraction mode of the system. And they find then that there's a ladder of evenly spaced breathing modes. Their energies are quantized, they're exact, so the collective modes of this gas, and their frequency is twice the harmonic trapping frequency. And another famous example of this is the Efimov state. So this is a situation where you have 3 very loosely bound, originally nucleons, and you look at the lowest energy of the problem. You get rid of all of the angular dependence, and you reduce everything to an S-wave state, and then the problem can be reduced to a single Schrodinger equation, a single effective Schrodinger equation. But now the coordinate here is the hyperspherical radius, so it's some sort of symmetrized version of the separations between all the particles. And so you get back to this 1 upon r squared potential again, and it has this scaling symmetry. And it was predicted in like 1970 by Efimov in the context of nuclear physics, but it was realized in cold atoms over the last 10 years or so. And so what you find is you get this scaling, you get these incredibly large molecules, very, very weakly bound, large molecules you see on these different scales. So this is an artist's impression. You still can't actually take pictures of these molecules, but this is a sort of popular press for it. And but what you find in this system is that this continuous symmetry, this continuous scaling symmetry is actually broken and becomes a discrete symmetry. And you get, so the symmetry becomes a geometric progression of bound states that reach an accumulation point at 0 energy. And they're related by this scaling symmetry, and this number lambda is 22.7 roughly. So that's Efimov physics. But this feature of Efimov physics, that this scaling symmetry is broken, actually turns out to be a very typical situation. So this is an example of what's called a quantum anomaly, and this is where quantum effects break continuous scale invariance of a classical Lagrangian. Okay, so this is very well known in high energy physics, but is less well known in the low energy communities. So examples are breaking of axial SU2 invariance, where the pion can have 2-photon decay. QED and QCD basically have broken scale invariance. These Efimov states I just talked about, and this scale invariance in 2D gases, they're all examples. So in fact, in all of these situations where you get this scaling symmetry, you in fact expect it to be broken by quantum effects. And so I mean beyond single particle, beyond mean field effects. And so in fact, this has been recently measured also in the 2D gas case, very recently. This came out about a month ago. An experiment where people looked at this breathing mode of a two-dimensional gas, and they found it was the frequency of oscillation was very slightly shifted away from this twice trap frequency that I said it should be at, according to this, if it truly had this SO2 scaling symmetry, according to Pedievsky and Roche. Okay. So let's look at this problem using this point particle effective field theory. Okay, so let's set the problem up a little bit, and what it comes down to is an ambiguous boundary condition in this 1 upon r squared problem. It's not obvious what boundary condition to apply. So when you solve the hydrogen atom, you don't have to think. I mean, Schrödinger had to think; he solved it, but it's a problem you don't have to think too hard. You basically you find these two independent solutions, and you choose the one that's finite at the origin, right? That's the boundary condition you can use. And it's sort of given to you on a plate, and you don't even think about it, you don't worry about it. But it turns out for many other problems, and this one included, you have to work a bit harder. So here's our 1 upon r squared problem. So we've got the angular momentum barrier, but now we add on now this 1 upon r squared potential. And we look at the general solution of this for very small distances. Okay, so we can have this power law solution. Substitute this in, and you get this then, the powers here are are given by S plus and S minus here. And there are two regimes. So there's a subcritical regime, where these are both real numbers, where S1 and S2, S plus and S minus are both real. And there's not so much of a problem, because the two solutions are distinct. They're different. And typically you would choose the one that's not singular at the origin. Okay? But when you go into the so-called supercritical regime, this gamma greater than 1/4, that's the fall to the center regime, then you have a problem, because you find that both the real parts of you basically get to the exponents here are complex conjugates of each other, and the real parts have the same sign. So they either diverge or don't diverge, but they both do it in the same way. And so there's no, how do you choose between them? You don't know which one of these things to throw out, or what balance to choose between them. So you need some boundary condition, and we're going to be guided by this point particle effective field theory as to what boundary condition to choose. Okay, so basically we have this difficulty that these guys diverge in the same way at the origin, and we need some boundary condition to determine basically this ratio of C plus to C minus. And so what this point particle effective field theory to the first, if you just keep the first term here, and then you calculate your Euler-Lagrange equations, basically what it adds to your Schrodinger equation, your effective Schrodinger equation, is a delta shell term. Okay, at this particular, and we put it at our regulator distance, somewhere between the microscopic scales and the macroscopic scales. And so when you run through your Schrodinger equation, what this imposes is a boundary condition on your radial wave function. Okay, and this is, if you divide through by r, this is like the usual logarithmic derivative boundary condition. And it's applied at this, we applied on this Gaussian pillbox, okay? And it depends, and it's governed by this microscopic physics that goes into lambda here, okay? Okay, so basically what you do is by adding this boundary condition, we're going to break scale invariance because it's going to fix our ratio of C plus to C minus by adding on this extra boundary condition. And there's many ways to do this, and most people go for a self-adjoint extension. That's such that you get the system is not absorbing or emitting. It's the standard sort of quantum result you'd expect. But point particle effective field theory gives you a way to do this in a sort of automated way. So as I showed on the last slide, you get this extra boundary condition. But we don't have to choose this coupling constant lambda that's going to describe our microscopic physics. We don't have to choose it to be real. Okay, for instance, so the flux of particles to the center is given by the current operator here, and it just depends on the imaginary part of lambda. So lambda could be real, in which case we get a self-adjoint extension, or it could be it could have an imaginary piece, and then we can choose the imaginary piece to be positive or negative, and we either get a sink at the center or we get a source that's producing particles. Okay, but there's some more complication in this, and that's the following. So the point is that when we apply this boundary condition at this arbitrary point, this Gaussian pillbox, this scale here, it's up to us where we choose it, and the physics shouldn't depend on it. Okay, our low energy physics that we want to describe out at distances a shouldn't depend on where we apply this boundary condition. So that means that somehow our physical part of the theory, what we can actually measure is this ratio of the two amplitudes of the two parts of the solution. This is what's physically meaningful, because for instance, the scattering, if you calculate your scattering lengths and so on, they just depend on this ratio. So it shouldn't. So that this ratio of C plus C minus shouldn't depend on the magnitude of epsilon. Okay, and so what it means is that as you change this scale here, this coupling constant lambda should run. So it depends on the scale at which you apply this boundary condition, where you apply it. And so this is the hallmark of renormalization group. Okay, so we want that the derivative of this ratio C plus upon C minus. So we apply this boundary condition, and it gives us this condition, this relationship between our physical parameters, the ratio C plus upon C minus that defines our solution, and they're related to this lambda, but it should obey this condition, that this guy shouldn't depend on epsilon. And so what one finds when we apply that is this flow equation for how lambda flows as a function of epsilon. Okay, and so what you get is these renormalization group flow equations. Okay, so what you get is in the subcritical case. How did I derive it? It's a bit of a long story, and I'll tell you afterwards. But it's this equation would take me a few pages to derive. Yes? Yes. Okay, so And what you get is the following flow diagram. So basically, you get this flow from UV to IR, from very small scales to large scales. So what I'm plotting here is this microscopic coupling lambda. Okay, this is the imaginary part of it, and this is the real part of it. If we want to keep it real, then we just live on the real line here. Okay, but we're also allowed an imaginary part. And so you have these two fixed points. One fixed point corresponds to one of these two coefficients being 0, the C plus, and the other one, that's the UV fixed point, and then the IR fixed point corresponds to C minus being 0. So we have just one solution or the other at these two fixed points, but as we follow these flow equations, which describe exactly the same physics, the same microscopic physics, we just have to change the coupling in our effective theory as we change the scale. Okay, so the physics is the same all the way along any one of these trajectories. And what happens is, as you ramp up as you increase the strength of this 1 upon r squared potential, so you get fall to the center, you get the critical case. So you get these two fixed points, they annihilate and then move into the complex plane, and you get limit cycles. Okay, and this means that basically you get periodic behavior. You don't just flow from one fixed point to the other. You zoom around one of these limit cycles. One of them, this one corresponds to pure absorption right at the center, and this one corresponds to pure emission. Okay, so this means so this previously scale invariant problem, what applying this boundary condition does is it breaks the symmetry, it introduces a scale, but then our physical observables, we find that as we change the scale at which we observe the system, they will follow this sort of periodic behavior. Let me skip over this slide to okay, here we go. So here's a prediction. For example, so if you look at the absorption, okay, this is the absorption as a function of our strength of our 1 upon r squared potential, you find that you get a log period. It's not scale invariant. So this would be the classical prediction. It wouldn't depend on anything. It's just basically this constant. Remember, it depended on 1 upon k. So you multiply through by k, you just get a constant. But now, what this anomalous breaking of symmetry makes it log periodic. So you have this periodic oscillation. So this is a log scale here. Okay, so and these two fixed points, as I say, this one corresponds to a perfect absorber, and this one's a perfect emitter. There's also an exotic bound state. So because you have this, even in the case where you don't have fall to the center, because you have this delta function potential always has a single bound state associated with it. So you get a bound state associated even with when the wave function is actually repulsive, when you can't penetrate through this angular momentum barrier. And you can control this in this wire experiment by basically the voltage. You can control the size of this bound state. All right, and so what one would need to do in the experiment, for example, is trying to see these effects, is control the absorption, control the microscopic physics. And one way you could do that is surround this wire by a repulsive laser beam, shine a sort of hollow laser beam around it, and this will control your absorption. It basically shields the system. Then you would see this. Because basically the experiment, they were stuck at one of these fixed points here. They got the classical result up here, they're fixed. So you want to move yourself away from this fixed point. Okay, that was fall to the center. Fall to the infinity, so I'm not going to discuss it. It's on a poster, but basically just to advertise very briefly, the idea is you have the Schwinger effect, Schwinger pair creation, where that's a case where you put an electric field on vacuum, and you start, once you make the electric field strong enough, you start producing, the vacuum is unstable to producing positron-electron pairs, and you start separating charge, and you can describe that, at least classically, through the Klein-Gordon equation with an electric field in it, and you can transform that, if you look for stationary solutions, you can transform it to the time-independent Schrodinger equation, but with an inverted harmonic oscillator potential. And so we call this fall to infinity because particles will fall off to infinity. And again, there's a hidden symmetry in this problem, SU11 symmetry. So go see Sriram if you want to know more about that. Okay, in my last 5 minutes, quantum catastrophes. Okay, what are these guys? So remember we had this general solution at small r. And now we pay more attention to this solution. So let's look at the case where we have the fall to the center, okay? So basically zeta is imaginary. Then we can have a divergent amplitude depending on the dimension. So d here is a dimension. So in 2 dimensions, actually this part goes to what you the rest of it has this, you have this r to the power some I to the some, so you get basically some complex power here, which you can rewrite in terms of this exponential of a log. And this means that the phase of the wave is undergoing a logarithmic singularity as it falls to the center. So the phase is oscillating faster and faster until it's undefined. Okay, so this is an example of a singularity where phase loses its meaning. And indeed, that shouldn't surprise us too much because phase is a very classical concept. There's no quantum operator for phase or no Hermitian quantum operator for phase. So phase is actually a rather semi-classical idea. And so this is getting into the Michael Berry's territory, where he asked the question, when do we need to second quantize waves in order to avoid singularities? And he has the example of where you have phase singularities, basically vortices in optical waves, where phase, again, breaks down, phase takes all possible values, and where the quantum vacuum should rule together. And he did this with Mark Dennis. So an example of this, which is close to the topic of the current, this fall to the center business. So this is an idea by Ulf Leonhardt. This is when you have, and indeed this fall to the center, it turns out can describe also motion near the surface of a black hole. So what you find is that the wave number grows inversely with the distance from the black hole. And so again, you get a logarithmic phase singularity coming up. And so he coined the term that this would be a quantum catastrophe. And the way he claims that this is resolved in nature is basically Hawking radiation. That it doesn't matter because phase is a classical idea anyway, and we know we need to go to a second quantized field, and the way nature gets around it is it produces these photon-antiphoton pairs. However, I mean, the end story is it's okay, but it's not okay in ordinary single particle quantum mechanics. So single particle mechanics will break down. That again is a whole story. It means you prepare the atoms in a superposition of their internal states such that you get a sort of polariton which is stationary inside the gas, and you can have light basically stop. So it's absorbed, but it's not absorbed. The gas is so the light is in a coherent superposition of the internal states of the atoms. It's a very nice thing, but it's a whole subject. Okay, so 1 minute. Okay, so just to say what is lying behind this idea of a quantum catastrophe is where you get singularities. So sort of Michael Berry's idea is, when do you need to second quantize a wave to get a singularity? Well, the first question you could ask is, when do you need to first quantize a wave to get rid of a singularity? So if you have ray optics, then you get these singularities, which are called caustics in optics, which are singularities of the ray theory, and you may have seen them in your coffee cup. And these aren't just random things. It turns out they're described by catastrophe theory. So it turns out we know what to do in this case, okay? We have the ray theory. We say, okay, that might be singular along this caustic line here, but we can go to the wave theory. And it turns out that this cusp singularity is decorated by this interference, a universal interference pattern called the Pearcey function, and everything becomes nice and smooth, and you get this oscillatory interference pattern. So the singularity goes away, but really what we're asking the question is, are there situations where even this sort of pattern becomes singular? And I won't have time to talk about it, but I'll just flash it past you to say, yes, so there's Ulf Leonhardt's idea in this fall to the center, but here's another one where you have two Bose-Einstein condensates in a double well potential, and you're interested, so it's basically a two-mode quantum field. All the particles can live on one side or the other, or you could do this in their internal states. So it's basically the simplest non-trivial quantum field you could have, a two-mode quantum field. And you suddenly put these two condensates into contact. Oh, okay. That's destroyed my okay. Let me see if I have another picture of it. Damn it, that's taken the punchline away. Wow, okay. I have to tell you what was in this picture. So basically, in this picture, you have a nice example of a Pearcey function, but it's in Fock space. So it's not in real space, it's in the number difference space between these. So these two condensates are defined by the number of particles on the left or the number of particles on the right. And you also have time, so you have a two-dimensional space. So you would have, along this axis, you have number difference, and along here you have time, and you get this Pearcey function, but it's in Fock space, and it's an example of what I call a quantum catastrophe. So you need to second quantize the system. You have to worry about the fact that that the atoms come in discrete lumps of one. If you just let them be continuous, you find that you get singularities, but it was all in that picture. Oh well. All right, so where's my conclusions? Conclusions, here we go. So what did I say? I told you about the inverse square potential, and I said, as an example, it has although it appears at first sight to have a classical scaling symmetry, in fact, it has a quantum anomaly in it, and it can, and it has been realized in the laboratory, for instance, in the Efimov states, and it has, but it can have non-self-adjoint extensions, and that's what we're trying to extend it to describe, say, these particles being absorbed onto wires and things like that. So we still want to see this log periodic absorption in this exotic bound state. And the wave function is an example of a quantum catastrophe. So you can ask Michael Berry more about a quantum catastrophe when he gives his talks next week. Okay, thank you.
Great. So I guess time for a couple of quick questions.
My quantum catastrophes come into every one of my talks, yes. The front end was different, but the back end was the same. Yes, is it the coffee break now? No, there's more. So you can't go and stare. Otherwise, I suggest you go out and you hold your coffee cup and stare at it.
Hello. Yeah, I didn't quite catch the idea, your comment about this Hawking radiation and connection.
Ah, okay. Yeah. So the idea here, okay. So the idea is when you calculate if you have this classical wave propagating towards an event horizon, you find that its phase starts going faster and faster and faster, and then it eventually takes all values, such that the idea of phase really breaks down. There's a singularity at the horizon. Personally, I don't like singularities. I like to resolve them. I think everything should be smooth. But you could say, well, it's not really a problem because that's a problem of our classical wave theory, like Maxwell's equations. Really, we should be dealing with a quantum field theory. And so then to resolve this problem, you need to go into the fact that photons exist. And so when you really look at quantum optics, there's no such thing as a phase operator. You can fix one up and it emerges in the classical limit, in other words, the Maxwell's equations, but it's not there in the fundamental theory. And so associated with this singularity turns out to be pairs of photons being produced. And that's kind of this slow light story that the system produces these pairs. So in the fall to the center thing, the idea for the experiment would be you have a Bose condensate, and you let that fall to the center on this wire. And so you're not creating atoms out of vacuum, because that takes a lot of energy. Okay, what you're doing is actually just exciting atoms out of the condensate. So the condensate behaves like a vacuum, and you excite pairs of atoms. And so there's an analog to Hawking radiation there. But that's a whole other story.
There was one thing that wasn't totally clear to me. So with the
Only one thing.
Only one thing, one of many things. But
Oh, dear.
so with the existing experiments from the Schmiedmeier group, were there things in the experiment that they saw that they couldn't understand, but you can now explain using the effective field theory, or there are new things?
No, they're new.
need to measure?
It gave extremely bland results. So that they reproduced precisely the classical result. So they saw basically this line here. So they were completely the perfect absorber. So yeah, they didn't see this log periodic behavior. So we're trying to get them to.
And what exactly do they have to do to see that? Like,
well, so basically shield the wire. Okay. So it's not such a great absorber. And they were also on a rather classical gas. So they weren't an ultra cold gas. Okay, they weren't a condensate or anything like that.
anything else? Well, let's thank Duncan again.
Yep.